Banerjee from Data Ops team, and I belong to the AWS squad. I'm working as a data engineer at XenonStack, and today we are going to discuss Apache Sedona. This was assigned as an experimental Saturday task because we faced some challenges while working on a project, and this Apache Sedona gave us the opportunity to explore geospatial data and come up with a solution to the problem statement. So let me explain the problem statement that we faced while working on the project. We were initially ingesting large amount of geospatial data, and that was required to be processed further for analysis. Initially, we were using Pandas UDF to process the data, but that was really heavy on memory and taking up a lot of processing power. And eventually, it was resulting in a lot of cost. In order to resolve this issue, we were supposed to find a solution. We tried out multiple solutions and did our benchmarking. In the benchmarking, we found out that Apache Sedona was a very good solution. It is a geospatial data processing library built on top of Spark that uses very minimal amount of processing power and memory, and which resulted in cost cutting. Let's discuss about Apache Sedona. So Apache Sedona is a cluster computing system built on top of Spark. It provides out-of-the-box spatial RDDs. We can see we have 3 different types of RDDs here. There are other RDDs as well, but in this slide we can see we have 3 different types of RDDs. One is point RDD, another one is polygon RDD, and the other one is rectangular RDD. And we have spatial query processing and optimization layers as well. These layers are spatial range, spatial KNN, spatial join, and spatial sampling. And all these spatial RDDs and queries can be used through 3 different APIs. These APIs are native APIs of Spark, and since these are native APIs of Spark, we can also use it in Apache Sedona. The APIs that Sedona provides are Scala API, Java API, and also PySpark API. Here we can see several benchmarkings and other processing engines that provide geospatial processing on top of Spark and Hadoop. We can see in the first image that the peak memory consumption of Apache Sedona is relatively lower than other libraries such as Magellan and Spatial Hadoop. Since Hadoop operates on disk, that's why it consumes relatively less memory than Sedona. Otherwise, if we compare it with Simba and Magellan, we can see that Apache Sedona consumes less memory. In this slide, we can see the processing power of Apache Sedona, and we can see the time it takes to process the same amount of data. If we see the first one, for processing points, it takes very or negligible amount of time to process points. If we see polygons, again we can see it took almost 6 hours to process polygons in Spatial Hadoop, Simba and Magellan, whereas it took almost 1 hour to process the polygon in Apache Sedona. And same goes for lines as well. So we can conclude that Apache Sedona consumes less memory and it operates at a very high speed. Let's take a quick look at spatial datasets. If we see this dataset, we can clearly see it has 2 columns. The first column represents one of the points of a coordinate, and the second one represents the second point of a coordinate. And this represents points. If we see this dataset, we can see it represents 4 coordinates of a polygon. To be noted, when these datasets are loaded in Spark, they are of string type. But if we want to perform any kind of spatial operations on these datasets, we need to convert them to geometry type. Once these 2 datasets are converted to geometry type, this is how it looks. And in order to convert these datasets, we need to use some special functions that are provided by Apache Sedona. Let's take a look at geometry types and spatial SQL operations. Here we can see we have 2 columns, column 1 and column 2, that constitutes of the points of two coordinates. Once we convert these to spatial type, we should be able to see data points like these. Now, Apache Spark offers a couple of format parser to load data from disk to Spark data frame. After obtaining a data frame, user who wants to run special SQL queries will have to first create a geometry type column. In this example, we can see that these two columns are of string type. Once that has been converted to geometry type, this is the type of the dataset. It is of geometry type. Here we can see we have four spatial SQL operators. Let's discuss the first one, the constructor operator. The functions are used to convert spatial data columns to geometry type. In this example, we can see we have two columns which are of string type again, and then they are converted to point type. And this has been done using the stPoint function that is provided within Apache Sedona. And once we run this SQL query, it would turn these columns of string type to geometry type. In this case, the geometry type is point type. The second SQL operator is a function. These functions are used to calculate geometric results like area, distance, and length. In this SQL query, we can see that I have used the stDistance function that is provided from within Apache Sedona. And what it takes 2 points and then calculates distance between them. I have applied this function on the point shape. If we see, we have 2 points, 1.1 and 100.1. And once we run this query stDistance, it will calculate the distance between the 2 points. And for each row, we can see that the distance between the 2 points. The third SQL operator is aggregation functions. These functions are used to find aggregation between two geometry type data. Here we can see we have 3 aggregation functions. One is envelope aggregation, second is union aggregation, and third is intersection aggregation. In this one, I have used stUnion aggregation. This function is used to perform union on polygon shape in this case. Here we can see we have multiple polygon type rows, and once we run this query, we should get a multi-polygon. Now, in order to visualize how a polygon looks, we can imagine an area, maybe an area of our office. But if we want to consider, for example, multiple buildings or multiple shops, or we want to see what are the constituents of a building, then a multi-polygon can represent separate rooms, and inside a multi-polygon we can see we have 1, 2, and further we will have multiple polygons which represent other rooms inside an office. The fourth SQL operator is predicate. These functions return true or false based on equality, intersection, and other such parameters. We can see some of the predicate functions, and here I have used the contains. So in my case, I have 2 geometry type data. The first one is polygon shape, the second one is point shape. And this SQL query uses a function called stContains. This is not again a Spark function, it is a Apache Sedona's function. And what it does is that if these points are included inside these polygon shapes, then it would return true. And in case if the point lies outside the polygon, then it would return false. Here we can see that in the first data point it is true, which means that this polygon is included inside this point is included inside this polygon, and the others are not. That's why the first column is true and the other columns are false. Take a look at the join queries. The join queries in the Apache Sedona are a little different from Apache Spark. So what it does is that it finds geometries from A and geometries from B such that each geometry pair satisfies a certain predicate. Most predicates supported by Sedona SQL can trigger a range join. So in this example, we can see that we are joining two data frames. One is polygon DF and the other one is point DF. And these two will be joined based on these conditions. If each data point lies inside the polygon, then only this query will be satisfied and it will return a joint data frame which satisfies this condition. We can also see distance join. It is used to find geometrices from A and geometrices from B such that the internal Euclidean distance of each geometry pair is less or equal to a certain distance. For example, if we take a look at the first query, we can see that we have 2 point type data frames. And if we do st distance, then this join will satisfy the condition where the distance between 2 points is less than 2. We also have broadcast join, and it performs a range join or distance join but broadcast one of the sides of the join. This maintains the partitioning of non-broadcast side and doesn't require a shuffle. We also have predicate pushdown. Given a join query and a predicate in same where clause, first execute the predicates as a filter, then executes the join query. So in this case, the where condition will be executed first and the st contents will be executed in the second. Let's discuss some of the use cases of Apache Sedona. The first use case would be geospatial data processing. It is able to efficiently process and analyze large-scale spatial data, perform spatial indexing and operations, and joins. It can be used in multiple applications that provides location-based services. We can develop real-time location-based application, provide information about nearby points of interest, routing, planning, and geofencing. Another use case could be urban planning and management. We can analyze spatial data for optimizing city layouts, simulating scenarios, and identifying areas of congestion. Environmental analysis can also be done. We can analyze climate, pollution, and ecological data, monitor habits, and support disaster response planning. Business intelligence and analysis can also be one of the use cases of Apache Sedona. We can analyze spatial data for retail analysis, market segmentation, and optimal store location selection. Geospatial visualization is another use case. We can create interactive maps and visualizations, generate heat maps, chlorophyllets, and scatter plots. Internet of Things would be one of the major use cases as well. We can integrate with IoT systems for real-time monitoring, geofencing, asset tracking, and anomaly detection. Some of the benefits of Apache Sedona are: first one is integration with Apache Spark. It seamlessly integrates with Apache Spark for scalable big data processing. Another benefit would be advanced spatial indexing. Efficient spatial indexing techniques improve query performance. Another one would be comprehensive spatial operations. Support a wide range of spatial operations and functions for diverse geospatial analysis. One of its advantage over spatial Hadoop is that it processes spatial data in memory. It handles spatial datasets in memory, reducing disk I/O and improving processing speed. And finally, it is open source and it can be used for free under Apache license, enabling customization and broad accessibility. The integration of Apache Sedona will result in notable cost saving for the customer by optimizing compute and memory utilization. This Sedona optimization will allow for faster spatial operations and decrease memory requirements. As a result, the customer will achieve significant cost reduction in terms of infrastructure resource, enabling efficient processing of large-scale spatial data, while minimizing expenses related to compute and memory resources. At XenonStat, we dedicate our Saturdays on continuous exploration and experimentation on new tools. As part of one of my Saturday experiments, I was able to explore Apache Sedona and gather information about geospatial processing and management. Thank you.